All right, we have been talking about this problem for a long time. Let's finally go ahead and solve it in this video. In order to solve this problem, we're going to use this departure function that we just derived, and we're also going to need to assume an equation of state. So I'm going to assume that the van der Waals equation of state is the one that governs methane at this temperature and pressure. And van der Waals is the earliest cubic equation of state, so it's not quite that accurate, but it's very good for illustration purposes. So we're going to need the A and B constants for the van der Waals, which I've provided for you there. And we'll also need the heat capacity of methane, which I looked up for you in Appendix A2. So we'll also need to remind you of the energy balance. Remember, the energy balance is shaft work over molar flow rate is equal to molar enthalpy 2 minus molar enthalpy 1. And remember, we couldn't calculate this difference in enthalpy directly, so we had to break it up into 3 separate steps. So we said it was H1 star minus H1 plus H2 star minus H1 star plus H2 minus H2 star. All right, so if you're confused about where that came from, go ahead and rewatch the last video. All right, so we got 3 terms here. The first and the third term are going to be derived from the departure function. So I'm going to take a break and write that in. So I've just gotten the departure function from the last video. So remember, this is the form that I didn't show you the full derivation of, but it's the form that's most handy to use. So in order to use this, I need to first calculate what this dp dt term is. So for that, I need to look up the form of the van der Waals equation of state, and that is P is equal to RT over V under bar minus B minus A over V under bar squared. All right, so the first step in solving this problem is to take the derivative of this equation of state with respect to T. This is what I mean by the van der Waals equation of state is already solved for P, so I don't have to do any further algebraic manipulation to solve for the derivative. So dp dt at constant v. So v is going to be treated as a constant, so r and b are always constants, and if v is also a constant, taking the derivative of the first term is super easy. Because t is to the first power and it's in the numerator, the derivative of any variable to the first power in the numerator is just the coefficient of it. So it's r over v minus b. And then the second term, there is no t at all, so it's minus 0. So a over v squared is a function if v is the constant variable, and therefore I don't have to do any integration on the second term. All right, so I'm going to plug in r over v minus b into the derivative term, and I'm going to plug rt over v minus b minus a minus v squared into the p term. And that is going to leave us with a departure function that looks like rt z minus 1 plus integral of, so let's see, it's rt over v minus b minus rt over v minus b minus the minus is a plus, plus a over v under bar squared. And all this is integrated with respect to v. All right, the RTs cancel, so that's easy enough. Now I have to integrate a over v squared with respect to v. So just pretend that the v under bar is an x, and you can, if you don't remember this integral, you can look it up in the integral table, but you probably should know how to integrate simple functions like this that don't need u substitution. So the integral of this is minus a over v under bar. And if you didn't know that, don't get too self-conscious. I sometimes have to look these up just to make sure myself. All right, this is going to be the general form of our departure function for a van der Waals equation of state. So h minus h star is simply this term. Oh, and I forgot to add the limits of integration. So remember, v goes from infinity to v is equal to v. So I'm just evaluating this term. At v is equal to infinity, this term goes away, right? So it's not a big deal that I forgot, just being proper about it, making sure I don't forget about it. it should give me the same thing. So again, I plug in V under bar for the one limit, and that's going to give me the same thing that I already have. And then for the second limit, I plug in V under bar is equal to infinity, which makes that term 0. So that term goes away. So it's RT minus times Z minus 1 minus A over V minus A over infinity, we'll say, and that's 0. So that's what I'm talking about. So this term is equivalent either way. All right, next we have to figure out what this V under bar actually is for the two cases. So we derived the general form of the departure function. We now have to apply it in two separate places. So we have to apply it for the two states. So we'll need to calculate what V under bar 1 was. And remember, this is at a temperature of 600 K and 10, was it bar? I think it was bar, not atmospheres. All right, so because we have two intensive variables, we can calculate the third with that equation of state. So we need to solve the van der Waals equation of state. In other words, we have to say that P, so that's 10 bar, is equal to RT 600K over V minus B. The value of the B constant is, and my units are going to be off here, 4.306 times 10 to the 5. 306 times 10 to the minus 5. And I'm going to highlight the fact that my B constant here is in meters cubed per mole. Minus A, the A constant was 0.203 pascals meters cubed per mole over V squared. All right, so in order to solve this, I'd have to convert from bar to pascals. So whatever the conversion is. I'm not actually going to show you how to solve this because, as I've pointed out before, solving for V in an equation of state that's cubic like this is kind of a pain. So you can't really easily solve this algebraically, and you'll have to tell me whether or not you covered how to solve a cubic equation of state in Thermo 1 or not. But for now, I'm just going to assume that this is one equation and one unknown, and there's actually going to be three answers for V under bar. And usually two of them are imaginary anyway. So you'll have one true answer, but the fact that it's cubic means that there's actually three answers. So going ahead and assuming that you can solve this will get you that V1 is equal to 4.986 times 10 to the minus 3 meters cubed per mole. So if you don't believe me, go ahead and plug in this V under bar 1 into this equation. You should get the same thing on both sides. Again, convert bar to pascals. So you need to say that 1 bar is equal to 10 to the 5 pascals, and that should work out. And I just paused to try that myself, and it does indeed work out. So you'd find V under bar 2 in the same exact fashion. So you'd say, find V under bar 2 by saying that 10 to the 5 pascals per bar times 2 bar, that's P2, is equal to R. And R is 8.314 in the units that we need, joules per mole Kelvin, divided by, or times T2, which is 400 K, over V under bar 2 minus B, same B, minus A, same A, V under bar 2 squared. So plugging that in and solving for V2 gives you 0.1659 meters cubed per mole. All right, always do a sanity check. So the two specific volumes that I've found, which one has a higher specific volume? I've got a higher specific volume in the second case. So that means that my gas is taking up, the same amount of my gas is taking up more space, which makes sense at less pressure. So my temperature is decreasing as well, but my pressure is decreasing by more than my temperature is decreasing. So it makes sense that my specific volume has increased. I now have a less dense gas, taking up more space again. Next thing that we'll need to calculate is Z, the compressibility factor. So Z is defined as PV over RT. And with V underbar now solved for, you can now easily, readily solve for Z. So I'm going to skip actually showing you what those Z's are. And I'm also going to skip step 2, where we say that for the change in ideal gas, change in enthalpy of an ideal gas, H2 minus H underbar 1 star is equal to the integral Cp dt. So plug in my expression for Cp, and I won't show you the entire calculation. I'll just say I'll plug in the constants. So I got the constants for you there, but say it's in the form of integral of a plus bt plus ct squared plus dt cubed dt. All right, so remember how this is integrated from t1 to t2. You would perform that integral and say that at plus b over 2 times t squared plus c over 3 t to the third plus d over 4 t to the 4, evaluated from T2 and T1. We did these calculations in MEB, and I know that for certain, so I'm going to skip the mechanics of actually doing that. I hope I showed you how to do this in Excel. I definitely always recommend Excelling to do these calculations, because it's a lot easier to actually see what your formulas are and you don't make a mistake. Then also you can copy and paste this formula as much as possible. So next time you want to do it, you just have to plug in your 4 constants, your T1 and your T2, and you get an answer immediately. All right, so I'm going to skip a couple of steps and put everything together. Hopefully I'm not skipping anything that's too important, but there's a lot of stuff here and I want to summarize it accurately. All right, so attempting to summarize here with color coding. Remember, this is our original energy balance that I've gotten for us here. I've color coded the 3 terms. All right, so the first term is the green term, and this is of the form of a departure function. So h1 star minus h is the departure from ideal states. We derived what the general form was. Notice that the only difference here is that it's flipped. So it's h1 star minus h in the energy balance, and it's h minus h star in the departure function. So therefore, evaluating what this h1 star minus h is, it's going to just flip everything. So it's minus RT1 times Z1 minus 1 plus negative A over V underbar 1. And all this stuff is stuff that we've calculated previously, or that we could calculate. Remember what Z is. Z is, actually, you know what? I'm going to simplify a little bit. So Z, I know it's simplified in the terms of the equation, but sometimes it makes it more difficult to do calculations. So Z times RT is minus PV, and then plus RT1. This is V underbar 1. So just performing algebra here to make it easier to see what we have to plug in. All right, so this is what we would calculate and plug in. Oh, sorry, P1 also has to be there too. P1. This gets plugged into the green term. The gold term is our CP term. So it's the integral of Cp dt. That is what I skipped. So just right above, you would calculate this whole thing and plug it into the gold term. Now the red term, sorry, one quick mistake I noticed I made on the blue term and the green one. I got to take a minus of the entire thing. So minus plus minus gives me 2 minuses, which is a plus. So this is what the green term should be. The red term is now just the departure function. So I'm going to take this one. This is the general form of the departure function. The red one I just copied through, and I'm going to put subscripts for 2 on all these. And I could multiply through the RT times Z again, and I could get P2V2 minus RT2 minus A over V underbar 2. All right, I'm going to give you a couple of answers just so you can check it. I'm not going to go through and show you all the calculations. This video is long enough already. The integral of CP, I got minus 9,000 289 joules per mole. The departure function, the green departure functions, this is going from 10 bar to low pressure. The green one should be 48.7 joules per mole. And the red one should be negative 20.5 joules per mole. All right, let me just quick do a pause and make sure everything makes sense. All right, I think everything is okay. So if I add these all up together, well, just real quick, just to kind of put our answers in context, notice of the green, the gold, and the red terms, the gold one is by far the largest in magnitude. And the departure functions kind of cancel each other out to a certain extent. All right, so I've got one's positive and one is negative. And even if you forgot about the departure functions for this particular problem, your answer wouldn't be off by that much. But that is not general behavior. And it kind of makes a lot of sense that H is primarily a function of temperature and to a lesser extent a function of pressure. But putting them all together and back into the original energy balance, shaft work produced per mole, if you add them all up, is minus 9,261 joules per mole. So that didn't feel quite as clear as I wanted it to. That problem was a lot harder to work out on a tablet than I was expecting. Just write your questions down. Be sure to bring them to our next meeting, which will be on Monday.